Hello, ladies and gentlemen. This is Mr. Briggs coming to you from the darkest depths of Mordor, or also known as my basement. Today's lesson is Stretching and Shrinking 5.3. It is the last of our really big lessons with similar shapes and using stretching and shrinking, and it takes place on page 82 and 83, problems A through D. And then your ACE problems are going to be 5, 27 through 34, 37, and 38. Your learning target is that I can use what I've learned about similar shapes to solve problems, continued, since we did that in the previous lesson as well. And I'm going to go over today a few ways that we can use similar shapes to solve real-world problems. Okay, so first let's cover practical uses. This doesn't need to be in your notes, but who's ever seen one of these guys? This is a surveyor. And surveyors actually make pretty good money. You have to go to school to become one, and it's your job using nothing more than a compass and maps and a really good set of measuring tools to accurately measure the land, accurately measure where someone's land begins and where someone's land ends, how wide rivers are, how roads should be laid out, how many miles it is from point A to point B, and which is the best way to get there. That is what surveyors do. They're sort of like explorers, but with math. And they measure really simple things like, well, where are we going to put the building, to things like the Grand Canyon. And this here right there is one of the few pictures we have of a surveying crew that mapped out the Grand Canyon. You can't actually take tape measures or yardsticks and go across the Grand Canyon. You have to use methods like the ones we are using to solve it. So now that we've covered practical uses of math and this use of similar shapes, I'm going to cover very impractical uses of it. So for instance, in our notes, we're going to put page 82, 83, lesson 5.3 notes, and we're going to use other uses of similar triangles. And we're going to put in the mirror method for finding heights. And you can use a mirror to find the heights of objects, as well as using shadows. And basically what you do is you lay out a mirror on the ground, a known distance from an object. So here we have Han Solo, the original space cowboy. He is standing, he puts a mirror 96 feet away from an AT-AT walker. And he walks backwards until he can see the AT-AT in that mirror. And what he's done is he's created a similar triangle, because light always reflects off a mirror at the same angle in which it enters the mirror. So that beam of light travels from the top of the AT-AT to the mirror up to Han Solo's eyeball. And we know that it is a known distance from the walker there, and we can use math to figure out how high it is. So let's do that now. We know that we are 8 feet away from the mirror. We know that we are 96 feet away from the mirror on this side. So all we do is 96 divided by 8, and we get 12. And what is 12? Well, 12 is our scale factor. We know that everything has to be multiplied by 12. We multiply that 8 by 12 to get 96, and we now multiply that 6 by 12 to get 72 feet tall. So this is a much easier method than using our shadow method. For one thing, you don't need to have sunshine to make it work. And you also can, use it a lot more practically in real-world settings. So you do not need to draw Han Solo. You do not need to draw the AT-AT. Go ahead and replace him with a stick figure, maybe, and maybe like a tree. Okay? There you go. Both work just fine. Okay, skipping ahead. Another way we can use distance is by we can measure distance as well as height of objects. And here's an example straight out of your book on page 82. I've just modified it a little bit. Here we have a river, and we do not know how wide this river is. And this can be a canyon, this can be a crack in Mount Doom, it can be anything, but we don't know its distance. It's something that it's not easy for us to measure the distance. So what do? Well, we find two objects on the other side of the river that we know the distance from. In this case, we have two trees on the other side of the river that we know are 45 feet apart. We also know that on this side we can plant two sticks 9 feet apart. And we position ourselves at a right angle back 10 feet. And we notice that if we're standing here, this flag lines up with that flag and we formed a similar triangle. So if we back that up a little bit, we've created two triangles here. We've created this big triangle located here, and inside it we've created another similar triangle right here. So we need to know what the distance of that river is. Well, we know that 45 feet and 9 feet are our known distances. And to get from 9 to 45, we had to multiply by 5. So 5 is our scale factor. So if 5 is our scale factor, that means we also have to multiply 10 by 5 to get the distance of our big honkin' triangle right here, the total distance. And we end up getting 50. But 50 feet is not the distance of the river. It's just the distance of this much larger triangle. So how do we find the distance of the actual river? Well, easy. We find our smallest triangle again and just subtract. Right? Because we are subtracting this section from the overall section, and we end up getting 40 feet as our overall distance. So these are two ways that we can practically use triangles and similar shapes to measure really awkward distances. And believe it or not, this is how people have measured the distance of stars and planets. This is the way that we have estimated the size of the moon and other bodies, basically by doing this very same thing, by comparing known distances to real distances and finding the scale factors and making really good guesses. So, ladies and gentlemen, your coursework for today is on page 82 and 83, problems A through D. And then your ACE problems, which are 5, 27 through 34, 37, and 38. If you need any help with this, make sure you ask your neighbors, make sure you ask me, Mr. Briggs, and have fun.